Familiar, you're familiar. So if you don't know by now, then you should probably get familiar.
Hello students, so welcome back to my YouTube channel. Okay, now in this video I am going to explain you the first chapter, that is motion. Okay, according to your first semester syllabus, the first chapter is motion. Okay, you take it as the part 1 for your reference, because you have to maintain a notes. Okay, online class notebook you have to maintain, and whatever the points I am going to discuss here, you have to write down that in that notebook as points. Okay, now let me start the chapter, so with some brief introduction about the motion. Okay, now tell me, so if you consider a body, so what kind of body you have to consider? It may be a small particle to a big planet also. Okay, so when the body is said to be in motion, the first question is when the body is said to be in motion, or let us say when the body is said to be at rest. Is it clear? Okay, so tell me with some example you can try to understand what is rest, what is motion first. Okay, suppose if you consider an object, okay, an object like let us say a duster. Okay, an object like a duster as a body. So when the body is said to be at rest, if it is not at all moving with respect to its surroundings, isn't it? With respect to its surroundings, it is not at all moving with respect to time. Okay, then the body is said to be at rest. Okay, similarly, if you consider a moving vehicle on the road, so it is said to be under motion. Why you are telling the body is moving on a road, let us say a vehicle? Because with respect to its surroundings, let us say the observer is standing on the platform, or there are some trees on either side of the road. Okay, with respect to all these surroundings, the body is changing its position. Continuously it is changing its position with respect to time. So in that case you have to consider the body is under motion. Okay, so now the question is, why some bodies are at rest always, why the bodies are in motion? So what is the cause? My question is, what is the cause for this body at rest and the body at motion? You have to say the force acting on the body, okay, is the main cause. If the balanced forces acting on the body in such a way that the forces acting on the body, the resultant forces acting on the body is not making the body to move at all. Okay, you don't say the forces are not acting on the body. You should not say no force acting on the body. You have to say the resultant force acting on the body is in such a way that the resultant forces are not allowing the body to move with respect to its surroundings. Then we can say the body is at rest. Okay. Similarly, if the resultant force is making the body to move with respect to its surroundings, then it is said to be motion. Okay. So basically you have to look at the forces. Okay, what are the total number of force acting on the body, and finally what is the net force acting on the body. So the effect of net force may be making the body to be at rest or making the body to be in motion. Okay, so you will come across this kind of discussion in Newtonian mechanics, you know. So basically you are discussing motion, you know. So this comes under the Newtonian mechanics. What is Newtonian mechanics then? So Newtonian mechanics is the relation between motion and force. Okay, we are discussing continuously all about the motion with respect to the force acting on it. Okay, so that relation what we are discussing in the subject is called Newtonian mechanics. Clear? Okay. Now let me start with the basic Newton's laws of motion in this chapter. Okay, as per your syllabus. So you heard about there are 3 laws: Newton's first law, Newton's second law, and Newton's third law. Okay, so let us start with the Newton's first law. So this Newton's first law is also called law of inertia, isn't it? It is also called law of inertia. Okay, so what is the statement? First of all, you try to catch the statement first. Okay, very simple statement, that is, every body continues in its state of rest or of uniform motion, okay, in a straight line unless compelled by an external force to change the state. That means if you consider any body or every body, okay, continues to be in rest always, continues to be in the state of its rest or uniform motion, isn't it? Uniform motion in a straight line only, unless, you have to understand that, unless compelled by an external force to change that state. Okay, so that means if you consider the state of the body in terms of velocity, okay, when the body is said to be at rest if velocity is equal to 0, when the body is said to be in motion if it is changing its velocity with respect to time, or you can say it is accelerated also under the force, right? So both two examples are considered in the statement of the Newton's first law. That means Newton's first law comprises two states, that is state of rest or state of motion. It comprises the two states of the body, state of rest and state of motion. Okay, and for these both the states, what is the main cause of the body? Inertia. You have to say inertia is the main cause. Okay, then what is inertia of a body, isn't it? The next question is, what is inertia? Okay, now let us consider the definition like this for inertia. Okay, so inertia is that property of matter by virtue of which, that means we are considering inertia as a property of a body, okay, property of a matter by virtue of which a body resists. That means it is not allowing. Resist means what? It is not allowing. Okay, resist a change of rest or motion unless compelled to change by external force. Clear? Change of rest, or it may be continuously moving, so motion. So both are resisted by the body itself. That means body is having some inherent property, internal property. It is always resisting to change its state of rest or motion. So that is called inertial property. Clear? Okay. So then how do you relate that inertia to the Newton's law? So according to Newton's first law, so it provides qualitative definition of force, because unless compelled by external force. So you have to consider the definition of force in Newton's first law itself. Okay, what is the main cause by the force? So you have to consider the qualitative definition. So this is basically obtained by Newton's first law, and this Newton's first law also recognizes the inertia as a fundamental property of material body. So we get the two things here. One is the cause of force and the fundamental property of a body as inertia. Okay. Okay, now let us see what is the force according to the help of Newton's law and the law of inertia. So let us try to understand what is force. Okay, force is an agent that provides or tends to produce acceleration, okay, or even retardation in a body, right? So once the force is applied on any particular body, either it should produce acceleration or retardation. What do you mean by that? Acceleration is increasing its motion in the direction of the force. Okay, retardation means it is opposing the motion. Even for that also we need the force in the opposite direction, isn't it? So the resultant of any force should be work like an agent that provides or tends to produce acceleration or retardation in a given body. Okay, now with an example you try to understand how the acceleration can be 0 or cannot be 0. Okay, see, you just consider a simple example. A book is at rest. A book is at rest on a horizontal table with respect to the earth, because always you have to say with respect to something else, some other body. So the book is at rest means what? The book is rest on a table with respect to the earth itself, okay, but not with respect to other planet. Why? Because planets are all moving, okay, earth is also moving. So with respect to other planet, earth may be moving. You should not consider with respect to some other planet. With respect to the earth itself, you can say the book is at rest. Okay, that is what you will come across in Newtonian mechanics. Okay, with respect to any surroundings, you have to justify whether the body is at rest or in motion. Clear? Now in this example, say this is the table we have and this is the book lying on the horizontal table. So what are the two forces acting on the body then? So very simple, we can say that the book is having certain weight, so that weight is always acting in the downward direction. Okay, so what is the cause for this weight? The gravity, isn't it? The earth is having the gravitational property. It can attract all the bodies towards the center of the earth. That you know very well, isn't it? So because of that gravity, the book is having the weight downwards, and the book is lying on the original surface, you know. So to this surface we can have a normal force acting in the opposite direction. Correct. So N bar is called normal force. W is the weight of the book due to gravity of the earth, and N bar is the normal force, and this force is also called contact force, and always perpendicular to the surface of the body. Okay. Now in this simple example, what do you say? Whether the book is moving? No. What is acceleration? Acceleration must be 0. So acceleration is equal to 0. Why? You have to justify now in terms of forces. You have to justify how the acceleration is 0 here. So very simple it is, because sigma F. What do you mean by sigma F here? Total force or the net force acting on the body. So that is the book here. Okay. So net force acting on the body, sigma F, that is given by the total force W bar plus N bar. But here N bar is acting in the opposite direction, you have to consider negative sign. Otherwise it is sum only. Plus of minus N bar is equal to W bar minus N bar itself, right? So that is equal to 0. So that you have to understand that. So W bar is equal to, in fact, equal to N bar in magnitude. Okay, Newton mechanics you can consider when they are equal forces acting in the opposite direction, so they can cancel each other. Okay, so magnitudes are cancelled. Okay, so this bar indicates actually the direction. W bar N bar indicates it is a force is a vector quantity having both magnitude and direction. With respect to direction, you have to consider the negative sign here. Okay, the magnitudes are 0. So even you can consider just magnitude also, like W bar W minus N. Okay, that is equal to 0. So because of this reason, you can say acceleration acting on the body is equal to 0. So in this example, not only one force considered here acting on the body, okay, multiple forces are considered here to justify the state of rest or motion, right? So Newton's first law, you can conclude that now Newton's first law holds good not only when there is a force on the body, but also when the net force is equal to 0. As per this example, we can say it is not only holds good when only one force is acting on the body, when the algebraic sum of the forces, that is called net force, is equal to 0. Clear? Okay. Now let us try to understand when the acceleration is not equal to 0 with another example. Okay. Look at the second example. A body sliding down on an inclined plane. So like this. So this is the inclined plane on which we have a body like this. Okay. So it is sliding downwards. Automatically it has to slide down. Why it is sliding down? Because of its weight itself. Okay. That weight should be greater compared to any other force acting on the body. Okay. What are the other force acting on the body then? Other than its weight. So of course the weight is always acting downwards like this, vertically downwards. The other forces means, so perpendicular to the surface we have a normal force N bar, and then if it is sliding downwards on inclined plane, it should have certain frictional force also, isn't it? So that always acting in the opposite direction to its motion, because friction is always opposing the motion and acting between the body and the surface at the contact point. Okay, at the contact surface between the body and the surface, there is a frictional force acting in the opposite direction. These are the forces acting on the body, you can say. Okay. So now in this situation, the body is sliding downwards. You have to understand that its weight is greater than all other forces here. What are that? Frictional force and normal force. It is exceeding both the forces and then it is sliding downwards, right? So you have to consider now W bar is the greatest force, greater than F bar and even plus N bar combined together. So frictional force and normal force, so both put together are smaller than its weight. Okay, sum of both the forces are smaller than the weight. That is why the body is sliding downwards here. Clear? Okay, so what is the total forces then? You have to consider the sum, isn't it? So that is W bar plus F bar plus N bar. So one of the four, that is W bar, is greater than F bar plus N bar here. So the sum cannot be equal to 0, even though the forces may be exactly in opposite direction or maybe in some other direction. You consider the magnitude. Okay, so with respect to the magnitude, we can say the sum of the force acting on the body is not equal to 0. Okay, is it clear? Sum of the forces, net force is not equal to 0. That is why the body is in motion. That means what is acceleration? It is accelerated or not now? Yes, the body is now accelerated. So this acceleration you cannot say not equal to 0, right? Clear? In this case acceleration is 0. Okay, here acceleration is not equal to 0. Okay, now let us try to understand the quantity called mass. Okay, so what is mass? So normally we define the mass of a body as just quantity of matter, right? Quantity of matter is called mass, right? Now in Newtonian mechanics particularly, we define the mass as the measure of inertia of a body. As we defined, the inertia is the inherent property of a body. Like that, mass is also some inherent property. Okay, so due to its mass only, we can see the different accelerations in the body. That is why according to Newtonian mechanics, mass is defined as a measure of inertia of a body, right? So now let us try to understand what is the impact of mass on acceleration, right? See, suppose the force that is particularly, you consider the same force. Okay, so you consider the force F bar acting on two different bodies of masses m1 and m2. Consider the example. The same force is acting on two different bodies of masses m1 and m2. Okay, so can you expect both the bodies will move the same acceleration? No, right? So when the same force acting on two different bodies of mass m1 and m2, okay, to produce two different acceleration, you will see a1 and a2. Then we see that the ratio of the masses m1 by m2 is equal to, it is inverse relation, a2 by a1, because acceleration produced in the body is inversely proportional to the mass. Okay, so greater the acceleration will produce for smaller masses. Okay, smaller acceleration for greater masses. Like that you will get the relation, and hence we can say, so by cross multiplication we can see that m1 is equal to either m2 into a2 by m1 or m2 is equal to m1 into a1 by a2. So that means what? We can find out one of the masses. Suppose if m2 is known for you, one of the mass is known to you, then with the help of the acceleration produced in the body, so we can calculate the unknown mass m1. Similarly, if m2 is unknown, if m1 is known, so take this relation and calculate the unknown mass m2. So in that way, acceleration produced in the body due to its mass will help you to find the unknown mass. Okay, so when both are acted by, the condition is whether both are acted by the same force. Clear? Okay, now so we can understand that here mass is always considered as a scalar quantity. As an inherent property, it must be a scalar quantity. Whereas if we consider its weight, okay, weight is said to be vector quantity because it is always acting downwards toward the center of the earth due to gravity, isn't it? It has the direction also, and hence weight is a vector quantity. So that means both mass and weight cannot be considered as same quantities. They are two different quantities. Okay, now at the end of this video, let us try to see some examples for Newton's first law of motion. Okay, that means on the law of inertia. So what are the examples we can see in and around in the daily life? Okay, so let us see some few examples to try to understand what is the impact of the law of inertia or the Newton's first law of motion. Okay, see the first example I am writing here as a book placed on a table continues to be at rest. Okay, this example already I have just now discussed here. A book placed on a table continues to be at rest unless somebody apply the force on it. Correct? Okay, somebody come and lift the book or somebody push the book, Okay, till then the body is always continues to be at rest on the table. So that is due to what? Due to the inertia of rest. Okay, that is due to inertia of rest, you can say. Okay, now let us say the second example. A passenger sitting in a bus gets a backward jerk if the bus starts moving suddenly. That means what? A passenger is sitting in the bus, but if the bus starts and moving suddenly, immediately what happens to the passenger? Okay, you will see that a backward jerk like this. Why? Because upper part of the body is still continues to be at rest, whereas the lower part of the body starts moving immediately along with the bus. That is why the passenger feels a backward jerk. Okay, that is due to the inertia of rest. Okay, similarly, look at the next example. A bullet fired on a window pane. That means, so on any glass pane you consider a bullet firing. So immediately we will see that a small hole, a clean hole is formed on a window pane, while a stone breaks the whole of it. Okay, very simple it is. You can see that on a glass pan, if you fire, you will get a small hole. Okay, a very clean hole is formed. Whereas the same window thrown upon by a stone, what happens? The entire glass will be broken. Correct? Why it happens? The bullet is having very high speed. Okay, the time of contact of the bullet on the window pane is very short duration. In that short duration, okay, the impact is not spreading over the entire glass pane. Whereas if you throw by a stone, so that stone is moving with very less speed. Okay, so the time of contact is larger. During that time, the impact is spread across the entire glass pane, it breaks immediately. Okay, so we can see that the example is again belongs to the inertia of rest. Okay, now a man jumping from a running bus. I think you already experienced. Suppose immediately if you jump out of the running bus, okay, what happens to you? Okay, he falls with this head towards the direction of motion of the bus, right? So you have to see that. So the moment you jump out of the bus, you will not get the backward jerk, you will get the forward jerk. Okay, that means your head is always moving towards the direction of the bus only. That means you have to stand properly, you have to run little bit. Okay, for small short distance you have to run along with the bus, then only you will come stable. Otherwise, if you try to jump and try to stand firmly, it is not possible. Okay, you will just fall down. Correct? So that is due to what? That is due to the inertia of motion. Okay, the body is continuously moving in the bus. Suppose if the body comes to rest immediately, it will not withstand, it will resist the rest. Okay, and it will try to continue the motion, and hence due to the inertia of motion, we will see that the body or the passenger is moving towards the direction of the motion. Okay, so law of inertia of motion, we can say. Similarly, in the long jump, okay, you know that the athletes, what they will do in the long jump, an athlete run a longer distance to jump longer distance. Okay, he has to run some long distance and then he will get a longer jump. That is because of the inertia of motion. He is taking the advantage of inertia of motion to jump longer distance, you can say. Clear? So that means the example 4 and 5 are due to the inertia of motion. Correct? Whereas the example 1, 2, 3, so they are all the examples for inertia of rest, we can say. So whereas these two are the example for inertia of motion. Examples for inertia of motion. Correct? Now look at some more examples here. Let's say example number 5 says the mud from the wheels. So that means you have to consider the mud which is stick to the tires of a wheel during the rainy season, you know that. So the mud from the wheels of a moving automobile flies off tangentially, okay, due to the inertia of direction. See, the wheels are rotating, you know, so in the direction of the rotation of the wheel itself, the mud is actually skidding and coming out of the wheels, okay. So that is just coming out of the automobile wheels immediately when the wheels starts moving, isn't it? That is due to inertia of directions, correct? Then similarly, the same example, the spark coming out of the grinding stone, okay, the spark, you know that the stone is rotating continuously. If you hold any metal or any knife, what happens? It produces some kind of sparks, okay. How the sparks are moving? Tangentially, okay. They try to move tangentially, and you can see the curves formed by the sparks also, correct? So the sparks coming out of the grinding stone appears to be tangential to the stone. So that is also due to inertia of direction again. So that means these two examples are due to the inertia of direction, correct? So these three examples are due to inertia of rest, and these two examples are due to inertia of motion. Clear? That is all about the Newton's first law covered in this first video. Okay, so I will see you in the next video with the Newton's second law. Okay.